Assalamu alaikum wa rahmatullahi wa barakatuh, and welcome to the Voice of the Cape Matric Revision Programme for 2022. I'm Konita Kamar, and my guest today is Muntasir Kadri from Intune Tutoring, and today we cover the subject of physics, focusing on vertical projectile motions. Assalamu alaikum to you, Muntasir.
Wa alaikum salam wa rahmatullahi wa barakatuh. How are you doing today?
I'm very well, Alhamdulillah. And yes, today being Monday, I know that many of our matriculants are at home as schools are closed for today. So I'm kind of feeling a bit jealous not being off today. But I think it's also, quite nice. So now we have our students who can view the lesson live. We do encourage you to send comments, and hopefully we can, maybe our facilitator would be able to respond to that. If not now, in the next lesson. So I welcome you to the session and now hand over to Muntasir to proceed.
Okay. So, as per introduction, we will be busy with vertical projectile motion. Okay. A lot of students tend to struggle with these, especially equations of motion, but that usually comes down to the fact that they forget simple things like using a reference. Right. And we'll see how that um, plays out in these questions. So, if we take a look at the first question, in this example, they mention a ball of mass 0.06 kilograms is thrown vertically upwards from the balcony of a building 3 meters above the ground. Right, so here we go. Here's where the person is standing. Here's 3 meters, and they're throwing the ball vertically upwards. Now, this is a classic example of projectile motion, especially vertical projectile motion. Right? The ball reaches a maximum height of h above the ground as shown in the diagram below. Ignore the effects of air resistance. All right, so we got no resistance that we need to worry about to take into consideration. The first question is, name the force acting on the ball while it is in free fall. Well, this is pretty simple. We know that that force is the gravitational force. Gravity is always bringing things down. What goes up must go down, and that's due to gravity. In the next part, they show us a graph, and this often throws students off because this is where your concept of reference and direction comes into play. Because remember, velocity is a vector, and vectors have direction. So the velocity time graph below shows the motion of the ball from the instant it is thrown upwards until it hits the ground. 3.2, write down the acceleration of the ball at time t equals 1,02 seconds. Okay. So the first thing we do before we even approach this question, let's first analyze what the graph is telling us, and let's compare it to the picture. All right. Now, if we look at the graph, it's showing here that our initial velocity at time 0 is some maximum value over here. It's a positive value. And what is that telling us? If the value is positive, it's telling us it's moving in the positive direction. Now, if we look at this image over here, we can say that up is positive. Right? We're setting a reference, and we can say that down is negative. Right? Pretty simple stuff. Right? There we select our reference. Now, we can see that the ball initially, if you're throwing it initially and it's coming out of your hand and you throw it up, the maximum velocity is going to be the moment you throw it up. And as it goes up, that velocity starts to decrease till it gets to a point where it peaks and it stands still in the air for like less than a second, right? And we can see our velocity starts off big, it's going in the positive direction, and it's slowly decreasing. Now, how does that actually relate to our graph? Well, if you look here, we're starting off with a big positive velocity, and our velocity is decreasing till it gets to this point here at 1.02 seconds, where the velocity is 0. Now, at the maximum height, our velocity is 0. So we know from this graph that it took us t equals 1.02 seconds to reach the maximum height. Now, we know our velocity was decreasing, but as we carry on the graph, it shows us that our velocity is increasing, but in the negative direction, right? So we're having what's known as a negative increase. This is now a negative vector. Now, why is it negative? Well, it's negative because it's going down. So it starts off at 0 and it slowly increases. The velocity is increasing slowly due to the fact that there is acceleration due to gravity working on the ball. The same reason why the velocity decreases as it goes up, because of gravity. It reduces the velocity. We have a negative acceleration acting on a positive velocity, so that's going to slow the ball down. Okay, but of course, if we have a negative velocity and a negative acceleration, that means we're going to speed up going downwards. And that's exactly what we see here in the graph. Right? We can see our velocity increasing in the negative direction as time carries on. So that's how you analyze and identify a graph such as this, right, in comparison to your diagram. Now that we've done that, let me just clear this off. The question is, write down the acceleration of the ball at time t equals 1,02 seconds. Now, to calculate acceleration from a velocity time graph, it's important for you to know that if you want to calculate acceleration, for example, I'll give you some ideas from graphs, right? Let me just go to the whiteboard. I go here. Let me just open a new page. And we look at some ideas. So here's one graph. I'm going to give you 3 graphs. Okay. And the graphs you'll usually see in equation of motion problems or vertical projectile, you'll see we can have a position versus time graph, right? We can have a velocity versus time graph. And we can have a acceleration versus time graph. Okay. Now, let's say we look at this position versus time graph. Let me give this here, right? If we want to find out what the velocity is according to position versus time, we can simply just take the gradient of this graph. And we remember from mathematics that gradient is equal to delta y over delta x. Or in other words, y2 minus y1 over x2 minus x1. And if we look here at this specific point here, we will have an x and y coordinate. But we know our x coordinate is time and our y coordinate is position. So we'll notice something very interesting. That at this point we'll have, let's say we'll have, sorry, let me just erase that so you can see it better. We'll have a t1 and we'll have x1. And at this position, we could call it t2 and x2. x2. Now, our gradient, oddly enough, if you look at this, is going to be, if our y values are x, we can say x2 minus x1 over t2 minus t1. Now, look at this. This is quite interesting. Look at what we get. We actually get delta x over delta t. This form should look familiar to you. This is actually velocity, right? So here's the thing to note. If we're finding the gradient of a position time graph, we're solving for velocity. If we're finding the gradient of a velocity time graph, we are finding something called acceleration. And there's nothing for the gradient of an acceleration time graph, right? And if we go back now to the previous problem, that's exactly what we can do. We can just find the gradient of this function. So we select 2 points. Okay, now let's see what they do. Write down the acceleration of the ball at time t equals 1,02 seconds. So now we need a few pieces of information. So let's go up here. We are using velocity versus time. Do they give us a speed? No, they do not. So we just need to get 2 points. The problem with this graph is they don't give us 2 points. We have this point here, 1,02 seconds at for time at exactly 0 meters per second. So we do have something over here. And then here we have some value. At 0 seconds, it's maximum velocity. Okay. Now, how would we even go about this? So let's take a look at the memo. Let's just see here. So that's exactly what they do. Well, am I looking at the right question? Give me a second. 3.2, write down the acceleration of the ball at time t equals 1,02 seconds. Yes, we're calculating acceleration. Let's just see here, 3.2. Oh, sorry. 3.1, yes, is with gravity, 9.8 meters per second downwards. Oh, my apologies. I'm so silly. Okay, right. The acceleration will remain constant. Right. So yes, you can use gradient to calculate acceleration, but in this specific problem, it's vertical projectile motion. The ball is being thrown up and it's falling down. It's falling down with a constant acceleration due to gravity of 9.82 meters per second downwards. Always indicate your direction. It's very important, right? Otherwise, you can write it as negative 9.82 meters per second squared. Right. And if you look here, that's exactly what it is. It's going to be 9.82 meters per second squared. That is the acceleration of the ball. Right? It's still going to be the same. Gravity is still going to work on it all the same. Let me just zoom out. 3.2. Here we go. Yeah, 9.82. Then 3.3 is consider the areas A1 and A2 shown in the graph above. Write down the numerical value represented by the difference in areas A1 and A2. So we look at the image and we look at the graph. And we know that from this point to this point, the function reached a maximum height, right? Which is h, they call it h, right? And we started 3 meters above the ground. That's where we started. Right? And they are talking about areas. So in this instance, our answer is actually going to be 3 meters, right? And if we look here, I'll tell you now, we've got A1, we've got A2, right? This is 3 meters above the ground. This is where we started off at over here when the velocity was maximum. This is 3 meters off the ground. And essentially, if we carry on all the way down, right, we're starting at 3 meters above the ground. This is our velocity. And basically, the areas between these two, if we have to find the difference between area of A2 and A1, we would actually get 3 meters. And if we do check the memo, let's just double check here. There's our answer. 3 meters is the difference of the areas. All right. So now 3.4.1. Let's take a look here. Calculate the speed at which the ball is thrown upwards. And this is where we need to get our equations of motion. So if we just pull up some equations of motion over here, equations of motion, right? Normally they'll give you a formula sheet, but let's just pull up a few of them over here. Get some images going. Here we go, right? So here are our equations of motion that we can use. We got V equals initial velocity, final velocity plus A times T. This is position. And we can use any of these. So let's go back to this problem. So we need to calculate the speed at which the ball is thrown upwards. So if we're going to use, for example, 3.4, V is equal to U plus a T. Well, if we did use this equation and we had to calculate, then at this point, time is supposed to equal 0. We can't really use that because then we'll end up with a 0 value over here, and we're saying that the final velocity is equal to the initial velocity, which is actually true in this case, right? But of course, now we can't really use this equation. So let's look at another one. Let's see what other options are available, because we don't want to get an answer where it's just v is equal to u, and now we're still left with two variables. It's not going to work for us. So let's look for a different one. Is the one where we are able to use position? Yes, we are. So yeah, we can use v squared equals u squared plus 2as. Okay, so let's use that one. Let's go back here. So we're going to use, let me get this pen, v squared equals u squared plus 2a. Now, in this case, I said x, but we usually have it in the form of x, but we'll just use s here. So let's see. Initially, our distance of the ground is 3 meters. Right? So we can say, okay, v squared, speed at which the ball is thrown upwards. Yeah, that's correct. V squared. Initially, we start off with a velocity of 0. All right, we get 2. We got negative 9.8 meters per second minus 2 times 3 meters. And we'll see if this all works out. We get v squared. Okay, we can't actually use the negative value here. It's going to cause us some issues because we can't square root a negative value. I'm sure this is the equation they use. Let's just double check the memo. Because in the initial velocity isn't given to us, but it's safe to assume it's 0 because that's what you're starting at. And we'll see here, that's the gradient. Yeah, so VF is 0. Okay, so here's the equation they use. So they used VF equals VI plus A delta T. They're telling us that the final velocity is 0 and our initial velocity is unknown. Okay, so that's what the question is asking. Okay. And then they got negative 9.8, which is correct. And the time is 1,02 seconds. That's the change in time. I feel like something's a bit off here. 3.4.1. Yes. Speed at which the ball is thrown upwards. Oh, my apologies. See, I erased the information that was on this image over here, and I forgot that I completed it in. Okay, let's just do this because I'm throwing myself off without having the information inputted. That's another important thing to note. Always, there we go. Always input the information on your diagram. So I'm just going to do this so I can re-input it. Then I know exactly what I'm looking at. Let's add to a new page. There we go. Shrink this down. Now, let's input the appropriate information. So here, remember we spoke about this graph and we spoke about this image. Now, here we're starting with at time 0, we're not starting with 0 meters per second. So our u value is up here. We don't know what this value is, but we know that at 1.02 seconds, right? Remember we filled this in, and we said that the time is equal to 1.02 seconds. Our velocity initially over here is some value, right? And that we can tell from the graph, it's some value. And that's what we need to find. We know that our v over here is 0 meters per second at the peak. We know that acceleration is negative 9.8 meters per second because the acceleration is downwards. And what else do we have? We got time, we got that, we got that, we got that. Right, lovely. So we can just go ahead and substitute the values in. V equals u plus a delta t. And we've given delta t, it's 1.02 seconds. Now we need to make u the subject of the formula because that's what we're trying to find. So u is equal to v minus a delta t. So therefore u is equal to, our v is 0 meters per second at the peak. And at the peak, it's 1.02 seconds change in time. So we got this minus negative 9.8 times by delta t, which is 1,02 seconds. All right. And there we go. And now we should get a positive value for our initial velocity. So 9.8 times 1.02 gives us 9.996 meters per second. So we're essentially getting 10 meters per second. Okay, there we go. So that's it to solve for the initial velocity. Okay, speed at which the ball is thrown upwards. Now, they want us to calculate the height h. And this is where we use that equation. So we go back into equations of motion. Which equation will give us height? Well, you could use this equation because we've calculated u already. Right? Maximum height, let's just see here. Maximum height is where v equals 0. That's where the maximum height is. Okay, so let us take a look here. We could use this equation as well. There's actually quite a few we could take a look at. But I would say let's use this one because this one we'll be able to use the speed at which it has a maximum height. So let's use v squared equals u squared plus 2as. So I'll go here. So to calculate maximum height, we can go v squared equals u squared plus 2as. And s is what we want to find. So we rearrange this equation. S is equal to, so we can just say 2as is equal to v squared minus u squared. Therefore, s is equal to v squared minus u squared over 2a. And now we have our equation to solve for the maximum height at where v is equal to 0. Now we can plug this in. Our v squared, we found that at that point is 0. This is negative 10 meters per second minus 1 over 2 times negative 9.8 meters per second squared. Something seems a bit off here once again. I can already see that we're going to get a very small maximum height, so this equation might not be correct. Sometimes equations of motion are like this. You'll notice there'll be an anomaly and realize something is not correct. Yeah, if we go 10 divided by 19.6, our value is going to be too small. 0.5 meters? Really? It seems so small. It doesn't make sense at all. No ways. No ways that's 0.5 meters. So this formula is not correct. We can't use this either. So then we need to use the one with time instead. Okay, let's look at the one with time. Here we go. S equals, I should have looked at the last equation straight away. There's also the first one. Okay, so S, if we go here, S is equal to, let me go back here, half U plus VT. Okay. Half U plus V times T. Okay. This is going to make more sense. So our initial is 10. Our final was 0 at the maximum height. We did get 1.02 seconds. This is going to make more sense. And then we get 10 times 1.02, which is 51.5 times a half. And that gives us an answer of 5.1 meters for the maximum height. That makes a lot more sense. Now, let us take a look if that is correct. Scroll down. Where's the memo? Yeah, 10 meters per second was correct for that question. Right, this is still the same one. And so they get 5 meters, and then we must add the 3 meters on as well. So we were correct in our calculation. The only thing we forgot to add was the 3 meters at which we started. So if we go here, we can see here's the 3 meters. So if we only went up 5.1 meters over here, which is this section, right? This amount from where we threw it was 5.1 meters. And then there's still another 3 meters that need to be added. So the total value is going to be 8.1 meters for the maximum height. So be very, very careful with these questions. Of course, I'm trying to compress as much information as I can into one time, so I will make errors like these. However, take your time in reading through these, analyze everything, take a note of the fact that there's a 3 meter starting point, and then you add that on if they are asking you about maximum height. Now, let us go to the next question. Let's go back up. So, okay, so we calculated height. So the next question, after hitting the ground, the ball bounces vertically upwards and reaches a new maximum height in 1.1 seconds. Calculate the work done by the ground on the ball while the ball is in contact with the ground. So what they're essentially telling us is, if we look at this image, they're telling us, where's my pen? Just do this. They are basically telling us that the ball comes down, hits the ground, and it hits the ground so hard that it bounces up again and reaches a new maximum height. And we can assume, let's say that's the maximum height, and the ball comes falling down again, right? But this is its new maximum height, apparently. The ball came down, hit the ground, and there was a certain amount of work done by the ground on the ball to cause it to reach a new maximum height. Okay. So let's take a look at what the solution is, and we can discuss why it is that. If we scroll down, let's see, what question was this? 3.5. Okay. Scroll 3.5. Here we go. Yes, 3.5. 3.4.2. And not that one. Where's 3.5? 3.5? Just give me a second. What's going on here? So we're supposed to use energy, of course, because we need to find work done. So, right. Okay, reaches a new maximum height in 1.1 seconds. They don't tell us what the maximum height is, so we can't really use that. We can use, as it hits the ground, right? We know it hits the ground with a certain speed, so we've got mgh and mv squared. So we'll need to use half mv squared to find the energy with which the ball acts on the ground. So where is this memo for 3.5? So it's not these, we did those. 8.1, did those. 8.1 meters. It's all the same. That's the same. Huh. Seems like that. There we go. Okay, I found it. So what did they do to calculate the joules? So what they did was, they said, which is what we mentioned, work done by the floor is EK. We know that the change in potential energy is 0 on the floor. So if we go here, if we look at this image, right, clear this all off. Yeah, let's make some space here. So we know that on the ground, EK is at its maximum kinetic energy. And at the top here, potential energy is at its maximum, right? The equation for potential energy is mgh, mass times gravity times height. And the equation for kinetic energy is half mv squared. So in order to work out the value or the amount of work done, because work and energy are essentially the same thing, they are both measured in joules, right? So is energy. So if we can find the kinetic energy on the ground, then we are able to find the work with which the ground is acting on the ball, right? So if you take a look here, what do they do? So we know that our V final is supposed to be 0, and our V initial is some value, right? And the V initial is, of course, the the velocity with which the ball is coming off of the ground, because the ball is going to reach a maximum height again, a new maximum height, and that is at where Vf is equal to 0. So first thing we need to do is find the initial velocity with which the ball is coming off of the ground. Now here that we find that it's going to be 10,78 meters per second. It seems a bit odd because we have a negative over here, but we do know that it's going upwards, right? So that's why the value ends up being positive for the initial Vi over here. Okay, so they use this equation. Then once they have this, they can go ahead and work out the let me see here. They can go ahead and work out the next velocity. Okay, so we work out the next velocity. So we got Vf squared. So this is what we're working out. We're working out final velocity. Vf squared equals Vi squared plus 2a delta y. Right? And we know we worked it out here. Vi was 10.78 meters per second. They substituted in there. I see that they aren't using the full value, but it's fine. Plus 2 minus 9.8 times delta y, which is minus 3. Right? The reason they said minus 3 is because we are 3 meters below the original starting position. Remember, we selected, if we go back here, when we initially did the calculations, we selected this point as the official starting position of a position of 0 meters, right? And the new starting point is now here on the ground. This is, of course, now going to be negative 3 meters because we are 3 meters below where we originally started with this problem. And that's why they're using negative 3 meters in that equation. Okay, so here we've got negative 3 meters here, we've got that. And then we find that the final velocity is negative 12.60. And here they give us an answer of 12.6 meters per second. So now we have our two values available. We have our final velocity and we have our initial velocity, right, which is perfect. Now we can go ahead and plug this information into here. So they go ahead and we say, okay, the net work done by the ground is just basically delta EK. We don't even need to worry with a delta EP, to be honest, right? Because we're going to end up with a value of 0 for delta EP, for MGH. So they plug this information in because we're strictly speaking about on the ground, what work is done by the ground. This is half mv squared h. Sorry, not half mv squared h. Let me just get my pen. This is just half mv squared. So this over here is basically EK. I mean, you're basically going to end up with work equals half mv squared. In this specific case, they are actually speaking about delta v squared, or change in velocity squared. That's why we have this subtraction going on here. So our final was 10.78, and it seems like our initial was 12.602. So they went ahead and they substituted these values in. Mass is 0.06. I believe they said 6 kilograms. So this is 0, was it 6 kilograms? I think it was, yes. So that's divided by 1,000. Let me just check. 0.06 times 1,000. Or was it 60 kilograms? I think it was 60. Let's just double check. I wish I didn't have to scroll down like this, but okay. All right, and then they substitute the values in and we get negative 1.28 joules. And that will be your final value for the energy. So let us go up here. Give me a second. Okay, this is making it all very hard to do. Okay, here we go. And that is the work done by the ground on the ball while the ball is in contact with the ground. Okay, and that's what we're going to get. So our initial velocity would have been at the top, right, as it's coming down, and then final velocity would have been on the ground. So clear this off. Right, and that's how you calculate the energy. So let's move on to the next one. A small ball is dropped from a height of 2 meters and bounces a few times after landing on a cement floor. ignore air friction. The position time graph below, not drawn to scale, represents the motion of the ball. So once again, we need to now analyze this graph. So we've got a position time graph this time, not a velocity time graph. Right? So if you look at this, it shows that our position starts at positive 2 meters. We can see the ball starts at a height of 2 meters. Over time, it falls. Right? It drops, position changes, it gets less and less till it hits the ground at 0.64 seconds. It then stays in contact with the ground for a further 0.03 seconds before recoiling and bouncing back up again and reaches a maximum height of 1.85. Then it drops down, hits the ground. There's a 0.07 second gap before it bounces up again, and so on. And then it reaches another time value over here. Let's say define the term free fall. Well, free falling is basically falling with the speed of gravity. That is what free fall is. But let's see what the official definition is. Right? Because of course this is the definition you are going to have to give in your exams. Now I am trying to find. Here we go. So example 2, the motion of an object under the influence of gravity or weight only. I just want to do this. I just realized this would make my life easier instead of scrolling down every time. Second. There we go. Okay. And then I'll just use 2 tabs. Oh, this is going to be much easier. Back up here. Here we go. Okay. And that's the term free fall, motion of an object under the influence of gravity or weight only. And you'll get 2 marks for that. Right? Gravity is just acting on it. Next question. Use the graph and determine the time that the ball is in contact with the floor before the first bounce. And then we just subtract the times. We actually spoke about that. Your answer should be 0.03 seconds. And if we go here, we'll see that it's 0.03 seconds just over there. Right? They just subtracted the 2 times. Okay. Now, the time it takes the ball to reach its maximum height after the first bounce. Well, that's pretty simple. We just need to see what this peak is over here. All right? It needs to match up with whatever this time is over here. Okay. And let's take a look at what they said. So, so much. Let me clear this off. So if we look here, for 3.2.3, we use the equation of motion. We say Vf equals Vi plus A delta T. We know that our final velocity for when it reaches the peak is always 0 meters per second. Remember that when the ball reaches the peak, it's slowing down as it goes up, and it slows down till it reaches the point of 0 meters per second. This is due to the negative acceleration due to gravity. Then we have Vi. That's what we need to find out. So they just go ahead and they use this equation. We know acceleration is negative 9.8. We know it took 0.62 seconds. All right, and we can see here, if we go back to this image over here, if we go 1.9, if we go 1.90, should see your option 1, 0.62. Sorry, I was looking at the wrong question. 3.2.2, we're not working with speed. The time it takes the ball to reach the maximum height. Yes. So we know that the time, my apologies, it's very confusing. Members aren't too clear when you're rushing through. So this point here, this peak, is halfway between these times. So all we essentially need to do is add these times together. Right? We can say 0.67 plus 1.9, and we can actually just divide by 2. Right? Sorry, not add. We subtract these 2 values together. That gives us what this time frame is. Right? So we can just go 1.90 minus 0.67 minus 0.67. That gives us an answer of 1.23 seconds. And this point here is essentially halfway between those two values of 1.23 seconds. So we just divide this by 2. Right? And that tells us that it should be 0.62 seconds. Right? So it takes 0.62 seconds for the ball to reach the maximum height. And then what we do is we have to just add the 0.62 onto the 0.67. And we know that it took 1.285 seconds for it to reach maximum height. So let's take a look here. And there we go, 0.62 is our answer. Easy peasy. Right. Now, let us take a look at the next one. The time it takes the ball to reach its maximum height after the first bounce, we said that the speed at which the ball leaves the floor at the first bounce. So there we go. The speed at which the ball leaves the floor. So we know it took 0.62 seconds to reach the maximum height. So this is the equation they use. So we're back here to 3.2.3. We want to calculate VI, the speed at which the ball leaves the floor. We know that if we use our peak value speed, which is 0 meters per second, and we know it takes 0.62 seconds for it to reach that peak, we can just substitute the values into this equation because we have the variables needed, and this is the unknown. And then we find that the answer is going to be 6.08 meters per second. Fairly simple as well. You just have to be careful with the analysis of your graph. That's it. Right? These questions are fairly tricky, but do not be deterred. I promise you, practice will make you so much better at it. And let's see, the time indicated on the graph, 3.2.4 T. Okay, so we're looking at the last problem before we close off. This memo and these questions will be available for you on the website. The link will be in the description below as well. So let's just look at the last question, 3.2.4. Time T indicated on the graph. Okay, let us go. Oops, no, I don't want to scroll through this before I get lost. Okay, so we scroll down and we'll find the answer over. Yeah, okay. So this is what we do. First, we have to calculate the initial velocity, right? And what velocity is that? Well, we're going to need this velocity over here. It's 1.9 seconds. What is 1.97 seconds? What is this initial velocity before it comes up and drops down here? So here we go. So they go Vf squared equals Vi squared plus 2a delta y. So what they're doing here is calculating the initial velocity. Our acceleration is 9.8. Our delta y is negative 1.2. Where did that value come from? Over here. Right? Here's the maximum height of 1.2. Our delta y is negative 1.2. It's 1.2 less than that. Right? So that's what we'll call this position over here. Okay. That's what they use there. Oh, this is if we took downwards as positive. Sorry. We're obviously taking upwards as positive, so we use the second equation. So Vf squared equals Vi squared plus 2a delta y. At 1.2 meters, which is the peak, we know our V final is 0. So we can calculate our V initial, and we find it to be 4.85 meters per second. And we're speaking about this point over here. Right? Here, the peak is 1.2 meters. We know that at this peak, it's Vf is equal to 0. We know that the time here is 1.9 seconds it took to get to this point. 1.97. And all they do is they go ahead and they substitute this in, and we find our initial velocity. Easy, no problem. So now, we take this equation, we pull it over here, and now we're going to calculate the time delta t. So now we use this one over here, where upwards is positive. So delta y is equal to Vi delta t plus half a delta t squared. And all we're doing here is we're just going to make delta t the subject of the formula, and we substitute our values in. Well, the highest peak at that point is 1.2. Vi, we worked it out to be 4.85, substituted in there. Delta t, we don't know, we leave it as is. A half, negative 9.8 for acceleration, delta t squared. As we can see, this already looks like a quadratic equation. We got delta t squared, delta t, and 1.2 over here. But don't worry, there's no factorization involved. all we're going to do is we're going to remove delta t as a common factor, and we're going to get it. We're just going to calculate these out, and then we're going to end up with delta t equals 0,4898 seconds. Right? Then we take that value of 0.5 and we add it to 1,97. Notice they're saying 2 times this value, 1.97 plus 2 times this value. Why are they saying 2 times this value? Well, if we go here, right, we'll see that this is the end time over here. This time that we calculated here is the time for it to reach the peak. Right? It took 0.5 seconds because we're using peak values here. It's the time it took to reach this point here. Right? So we calculated that as 0.5. But obviously it takes another 0.5 to reach this point here. Right? If this is 0.5 over here, if this took 0.5 seconds to find this peak, then it's another 0.5 seconds left over because it's halfway. And then we just say 1.97 plus 0.5 times 2, which is exactly what they did here in the memo. Right? It's exactly what they did there. And we end up with a value of 2.95 seconds. Okay, so that is it for us today. The link to the questions and the memo will be in the description below. I hope the session was helpful. Please enjoy the rest of your day and the public holiday that's coming up. And assalamu alaikum wa rahmatullahi wa barakatuh.
Walaikum salam wa rahmatullahi wa barakatuh. Walaikum salam wa rahmatullahi wa barakatuh to you, Muntasir. Shukran for a very informative session today, and we look forward to having you back next week, inshallah. You have a wonderful day, and to you, the viewer, thank you for tuning in. As mentioned, all the information is in the description, including the link to notes, inshallah. From myself, Kanita Kamar, and my guest, Muntasir Kadri, we bid you farewell. Assalamu alaikum wa rahmatullahi wa barakatuh.